Hi everyone, Sherry Ann here, and welcome back to My Chemistry Hub. And today we'll be doing a CSEC past paper question. So let's go. Now, if you hear the rain, today is just a rainy day, and but we carry on nonetheless. So the question reads: radioisotopes are very useful in everyday life. For example, uranium 235 is used in energy generation because it produces large amounts of energy when the atoms split. State two other uses of radioisotopes and explain the importance of each. So carbon-14 dating is one other use. Carbon-14 dating is one other use of radioisotopes. So essentially, what it's used to do is to determine the age of plant and animal remains of up to about say 60,000 years or so. It's used to determine the age of age of plant and animal remains oh there remain up to 60,000 years old. But how does it do this? The thing is, it essentially makes use of the fact that carbon-14, that with the radioisotope, has a half-life of about 5,700 years old. 5,700 years rather. And what do we mean by half-life? Half-life is just what the name suggests. It's the amount of time it takes for the radioisotope to decay by half. So half-life, the amount of time it takes for the radioisotope to decay half its amount, or decay by a half. So that's one other use of radioisotopes. Cobalt-60 is another radioactive isotope that is very useful. Cobalt-60, another radioactive isotope that is very useful in radiotherapy. Useful in radiotherapy. Right? And radiotherapy uses radiation to control cancerous growth. So what happens is that the external radiation is carried out. So let me just jot this down so we have it here. So external radiation is carried out by directing a beam of gamma radiation by directing a beam of gamma radiation, and this is coming from the radioactive source, from a radioactive source, a radioactive source, and the radioactive source is the cobalt-60, and this is directed at the cancerous growth, right? So these are two other uses of radioisotopes: carbon-14 using carbon-14 dating, cobalt-60 used in radiotherapy. Okay. All right, so let's go on to the next question. The properties of elements can be explained based on their electronic configuration and hence their position in the periodic table. The electronic configurations of four elements P, Q, R, and S are as follows. You see there, P is 27, Q 282, R 286, S 2882. Outline the criteria for placing elements in periodic table, hence state the appropriate group and period for each of the elements P, Q, R, and S. Right. Essentially, they're asking us What's the criteria? They give us the electronic configurations of elements PQRS and ask us the criteria for placing them in a periodic table, and then asks us to state which group and period these elements would be located in. Okay, so get the gist of the question. So first, electronic configuration is essentially the arrangement of electrons in the shells of an atom, right? You see, electronic configuration, the arrangement of electrons in the shells of the atom. Right? So they ask us what's the criteria. We just get that out of the way to establish what is electronic configuration, and they ask us the criteria for placing elements in the periodic table. So periods are horizontal rows of elements numbered 1 to 7. So we just jot that down. Periods. Done. So it's horizontal rows of elements, elements numbered 1 to 7, right? All elements in the same period, have the same number of occupied shells. The same number of occupied shells. Occupied electron shells, of course. Occupied electron shells. So all elements in period 3 have 3 shells. In period 2 have 2 shells, right? That's essentially what it's saying. And all elements in the same period have their valence electrons in the same shells. All elements in the same period have their valence electron in the same shell. What I mean by the valence electron is the valence electron, meaning your outermost electrons. Right? So let's run to horizontal rows of elements numbered 1 to 7. What does elements in the same period have the same number of occupied electron shells? Meaning if you're in period 3, you have 3 shells and they have their valence electrons in the same shell. So if you're in period 3, your valence electron will be on the 3rd shell. That's essentially what it's saying. All right, so groups now. Groups are vertical columns. Vertical columns of elements. And so there are 18 groups in the periodic table and 8 have numbers. So you have 18 groups, right? 18 groups. And 8 of them have not 8 of them are numbered 1 through to 8, Roman numerals. So you have 8 of them, numbered 1 through to 8. Yes, it's Roman numeral, right? We know how the periodic table looks. And the thing about groups now is that elements within the same group have the same number of valence electrons. So the same number of valence electron. So for example, beryllium, calcium, magnesium, they are in the same group. So they have the same number of valence electron, which is 2. And also elements in the same group, the number of valence electrons is the same as the group number. That's another thing we want to bear in mind. The number of valence electrons is the same as the group number. So, for example, sulfur has 6 electrons in as 6 valence electrons, as 6 electrons in the outermost shell. So therefore, it's located in group 6. Okay, guys. So now let's get back. Now that we have that out the way, let's get back to the elements that they gave us. So they gave us P, which is 27, Q 282, R 286, and S 2882, right? And they're asking us to place them in appropriate groups and periods. No. So the last number in the electronic configuration represents the valence electron or outermost electron. So the last number represents the valence electron, right? And we just discussed that the number of valence electron represents the group that the element is located in. So based on the electronic configuration here, P will be located in what? You are correct. Group 7. Group 7. That's one. 5, 6, 7. Yes. And Q will be located in what? Group 2, of course, because it has a valence electron here too. R, group 6. Correct. You are correct. And of course, S will be located in group 2. Yes. So remember that the last number in the electronic configuration represents the valence electron. Valence electron represents the group that the element is located in. So that's how you make the link, right? So what about periods now? We discussed that the number of occupied electron shells represent the period in which the element is located in. I remember we were saying that the electronic configuration is the arrangement of electrons in the shells of an atom. So if it has two numbers in the electronic configuration, this tells us that yes, it has two occupied shells. Therefore, it is in period 2. Are we seeing the link? I hope we are seeing the link here. So the number of occupied electron shell represents the period in which the element is located in. So P has two occupied electron shell. Therefore, period 2. Q has what? 1, 2, 3. So period 3. R 1, 2, 3. Same thing. Period 3. And S 1, 2, 3, 4. Period 4. And that's how you would group them in the appropriate period and group based on the electronic configuration. On to the next question, or on to the last question. Elements P and Q react together to form a compound. Deduce whether this compound is ionic or covalent. Use dot cross diagrams to show the bonding in the compound formed and write its formula. All right, so elements P and Q. Okay, so I write it back. P is 27, Q, so what was Q? 282. So chemical bonding essentially involves the valence electrons. Remember, these are the valence electrons. The valence electrons. And the aim is to obtain a stable electronic configuration or a noble gas electronic configuration. And that is, what do they mean by that? Is that they have a full outer shell. For example, helium has two on its outer shell. That's the maximum that shell can hold. Therefore, it's stable. Our neon has 8 on its outer shell. That's the maximum that the shell can hold. Hence, it is stable, right? And they can achieve this. They can achieve this stable configuration by taking part in by bonding, right? They either share electrons. We all know this to be covalent bonding, or donate to another atom, or gain electron from another atom. Either donate or gain electron to obtain the stable electronic configuration, right? With that in mind, let's draw the dot diagram, or the dot cross diagram of P and Q to explain what's happening. So Q, we know is 282. So let's see if we can draw that. So Q, in the first shell, you have 2, right? So 1, 2. In the second shell, you have 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. On the last shell, it's 8. Last shell, you have 2. 1, 2. Let's draw P. Let me use another color. So P is 2, 7. So P first shell, you have 2, 1, 2, 2. The second shell, you have 7. 1. No, that's not what I should do. That's not what I should do. Remember, it's a dot. Remember, it's a dot cross diagram, right? Hope you're seeing. So we use the dots over actually. That's 2. That's 1, 2, 3, 4, 5, 6, 7. Right? So as I said, that to obtain this stable configuration, they either want to donate or gain an electron. So look at Q. Q has 2 on its outer shell. It will be to obtain the stable configuration, either it's going to gain 6 electrons to form the 8, or just give away the 2. It'll be easier to give away the 2 because P right here, right? P, to form a stable configuration, it's either going to gain 1 to obtain 8 or give away 7. And it will be easier just to obtain the 1 because you have Q here ready to donate 2. So give 1 here, right? 1 goes here. But P can only accept 1. So what we're going to know? Just draw another P atom, right? To accept the other electron from Q. 1, 2, 3, 4, 5, 6, 7. The other P, other. Yes. So that would, so Q has 2 to donate. P only can accept 1. So you need 2 P atoms. And then the overall, I'll go back to red, so can just be consistent. Q will be looking like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So it would donate. Remember, it's an ion now because it loses 2 electrons. Change my here. P on the other hand now would be like this. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Now remember, it got one from, it accepted another electron from P. So you'd have to, right? Just to show you what's happening. And remember, it accepted an electron. Oh, that isn't drawn properly. It accepted another electron from Q, and it's two of them, right? You end up with your compound being QP squared, right? Because you have two P atoms taking part in this bonding. So that's the end of our lesson for today. I hope you do learn something from what we just went through. So we went through electronic configuration, radioisotopes, and also chemical bonding as well. So thank you for joining us today, and come back again for our next video. Thank you.